We're going to kick this off with an introduction to the complex numbers. So the complex numbers are a family of numbers, and before we start working with them and all the things they lead to, we need to know what a complex number is. So we're going to start with the definition of a complex number, and then we need to know how to operate with these numbers. So we'll define addition and multiplication for the complex numbers, and then from there we can establish some basic properties for the complex numbers. So before we get going, let's get a little history of where this all started. So the first known example, so the first existing or example from a still existing document of someone working with what we now associate with complex numbers, the square root of -1, dates all the way back to the 1st century AD with Heron of Alexandria. But in his calculations, I believe he was working on the frustrum of a pyramid, if I remember right. In his calculations, he used +1 for the principal square root of -1, which we now know is not true, so kind of missed an opportunity there to become famous in the world of mathematics. And then from there, basically for centuries, mathematicians, anytime they came across the principal square root of a negative number, such as -1, they just considered that impossible or even absurd. However, in the 16th century, while working on trying to find the general solution to any cubic polynomial equation, mathematicians began to notice that you could work with the square root of -1 and end up with what we now call real numbers in those calculations. So they noticed that products containing the square root of -1 actually resulted in real numbers and numbers that they were used to working with and that they didn't consider impossible or absurd. So they started to kind of pay attention. It's like, well, wait a minute, maybe there is something to this whole square root of a negative. So rather than tossing them aside, they began to actually kind of keep them around in their calculations. Well, the actual term or name imaginary number we associate with René Descartes from the 17th century. So that's where that name comes. It's an unfortunate name because people think, well, if they're imaginary, obviously they're not actual things and numbers that don't have any meaning, which isn't true. So it's an unfortunate name, but the other numbers we called real numbers. And then since these were so looked down upon, we get this name imaginary number. And as far as using this lowercase I for the principal square root of -1 that we now use, we owe that to the mathematician Euler from the 18th century. So that was his notation. And that notation actually bothered mathematicians for quite a while. And then in the 1800s, a mathematician by the name of Hamilton, he reworked the definition so you didn't have to use that lowercase I, but his definition required that each complex number be thought of as an ordered pair, but those ordered pairs contain real numbers only, and the definition for complex numbers still worked the same way as Euler's. So, but nowadays, almost everyone just uses this lowercase I, so that's what we'll use in our brief introduction here. So let's start with the definition. It's the same definition you're given in almost any high school textbook with complex numbers. So this is where everything comes from, is the definition of what a complex number is. So we're going to use Z to represent a complex number, and Z this complex number will be defined as x plus yi, where x and y are elements of the real numbers. So x and y will be numbers that you're used to working with, real numbers, and then that lowercase I will represent the principal square root of -1. So I is defined to be the principal square root of -1, which, as you remember from your study of square roots, if I is the principal square root of -1, then if you squared both sides, that would imply that I squared is actually -1. And that was the whole idea, is that we needed a number that when squared came out negative. So Euler defined that to be this lowercase I. Well, x, since x does not have the I with it, we call that the real part of the complex number, since it doesn't have the I part. And it does have some notation. So we say x equals RE of z. So that represents the real part of z, or what we're calling x up here. And then y, since it has the I connected to it, we call that the imaginary part. So y is the imaginary part of z, and we denote that as im of z. So imaginary part of z, that's the y. That's the coefficient of I. Not really coefficient, I guess I is not a variable, but the other component here. And then just like this capital R represents all real numbers, this capital C will represent the collection of all complex numbers. So if you see this capital C, I'm referring to every complex number, or the collection or family of complex numbers. All right, so now that we have the definition, we need some basic properties. And these seem mundane, but they're important. So in mathematics, you have to lay down the foundation. You have to define everything meticulously and build upon it. So now that we have these new numbers, we need to start with things like, how do you know when these two numbers are equal? So equality under the complex number system, well, let's see how that's going to work. Let's say you have two complex numbers. We'll call the first one Z1, and it'll be defined as X1 plus Y1I. The ones just to note that goes with Z1. And then we'll have another complex number Z2, and it's defined as X2 plus Y2I. And we'll say that these two complex numbers are equal to each other if the real parts are equal and the imaginary parts are equal. So if X1 equals X2 and Y1 equals Y2. So much like the real number system, if the two complex numbers are identical looking, so their parts are identical, so X is identical, Y is identical, then they are equal to each other. Well, now we need to know how to operate with them. So let's start with addition. So how would you add two complex numbers? So again, let's define a Z1 and a Z2, and then to add these two complex numbers, we're simply going to combine the like terms, the matching components. So Z1 plus Z2, you would just add the real parts, so X1 plus X2, and then you would add the imaginary parts, so Y1 plus Y2, and then you put that together, and that would be the sum of those two complex numbers. So this right here, that would be the real part of the sum, and this part right here would be the imaginary part of the sum. So pretty straightforward. You just more or less combine like terms for addition. Well, how about multiplication? So again, let's define a Z1 and a Z2. So Z1 is X1, Y1I, and Z2 is X2 plus Y2I. Then if you want to multiply them, we're simply going to distribute. So although it's not really called distributing yet because we don't have that property. However, that's, when you look at it, that's more or less what's happening. So if you want to take Z1 times Z2, we define multiplication as this. So here's Z1, and we're going to multiply that by Z2. So we're going to define multiplication as the real part will consist of X1 times X2, and then minus Y1 times Y2. And the reason we have that is because when you go to take Y1I times Y2I, you'll get Y1, Y2, which is right here, and then I squared, which is negative 1. So that's why it's minus. And then we'll add to that. Well, then we take X1 times Y2I and Y1I times X2. So you'd have X1, Y2, X2, Y1, and they both would have an I. So you can factor that I out or think of it as factoring, even though we haven't defined factoring yet. So we end up with X1, X2 minus Y1, Y2 plus X1, Y2 plus X2, Y1, I. So this is the actual definition of multiplication. So no proof here. That would just be the definition. That's how we have defined multiplication in the complex number system. Well, now that we've defined addition and multiplication, we need to get all the other properties we're used to having. So we'll start with the additive identity. So in the real numbers, it's 0, because if you add 0 to any real number, it does not change that real number. So we want something similar in the complex numbers. So the additive identity, once again, is going to be 0. So the additive identity is going to be z equals 0 plus 0i, which is 0. And that is the identity because using our definition of addition, if I take that number, 0 plus 0i, and add it to any complex number, I get that same complex number because 0 plus x is x and 0i plus yi is yi. So just like the real number system in the complex numbers, z equals 0 or 0 plus 0i is the additive identity. That's what you can add to any complex number and it will remain unchanged. Well, now that we have an additive identity, we can define the additive inverse. So if you pick any complex number, we'll call it z1, there will exist a negative z or an opposite z such that when you add, so call that z1 also here. So for each z1, so each complex number, there exists a unique opposite of z1 such that z1 plus its opposite will give you the identity, the additive identity. So this is simply saying that if you have a complex number, there will exist an opposite complex number that their sum is 0, the additive identity. So if z1 is x1, y1, then its additive inverse will be negative x1, negative y1i. So if you add them together, you get x1 plus negative x1, which is 0, and then y1i plus negative y1i will be 0i, which is 0. So their sum is the additive identity, which, looking ahead, is how we will define subtraction, is by using this additive inverse. All right, let's move on to multiplication. So in the real numbers, positive 1 serves as the multiplicative identity, because if you take 1 times any real number, the real number remains unchanged. So in the complex number system, it's also going to be positive 1, because if you define, or if you take the complex number 1 plus 0i, which would be 1, the real number 1, you can take that complex number, 1 plus 0i, times any other complex number, and using the definition of multiplication, it will keep the complex number unchanged. So if you take 1 times x, you get x, then you get yi plus 0i, so that's yi, and then you get, let's try that again. 1 times x is x, and then you get 1 times yi plus 0 times x, which would just be yi, and then 0 times that would be 0. So yeah, we end up with x plus y I when you multiply those together. So z equals 1 times any complex number leaves that complex number unchanged. So the multiplicative identity will be 1. Well, now that we have the multiplicative identity, we can define the multiplicative inverse. So if you take any complex number z, as long as it's not 0, there will exist a z negative 1, which we're going to call the multiplicative inverse, such that when you take z times its multiplicative inverse, you get positive 1. So in the real number systems, we also call this a reciprocal. So this would be, for the complex numbers, we call it the multiplicative inverse, which is also what it's called in the real numbers, but reciprocal is a popular term also. So as long as you don't have 0 for the complex number, there's going to exist a multiplicative inverse so that you can take that number times its multiplicative inverse and come out to get positive 1, which is the multiplicative identity. All right, so how do you find this multiplicative inverse? It's not as easy as the additive inverse because you just do the opposite of those real numbers, x and y. But how do you come up with this multiplicative inverse? It's actually not as obvious as you might think. So let's see if we can't figure out how to come up with a multiplicative inverse for any complex number. So we're going to let z equal x plus yi, we want its multiplicative inverse, which will have be a plus bi. A and b are real numbers, such that, so we want a plus bi to be a number that if we take z times that z negative 1, it'll come out to be positive 1. Or another way to think about it is, I want x plus y I times a plus bi to come out to be positive 1, which would be 1 plus 0i. Well, if I multiply these two together, so if I take x plus yi times a plus bi, if I multiply those together, I would get ax minus by plus bx plus ay I and we want that to be equal to 1 plus 0i. So if we equate the real parts, that means we want ax minus by to equal 1. And then we want bx plus ay to equal 0 if we equate the imaginary parts. So the real part should equal 1, and the imaginary part should equal 0. If I solve this first one for a, so I'm just going to solve this first equation for a, we get 1 plus by divided by x. And if I solve this second equation, we're going to solve it for b, but we have a system here, so they both use a and b, and they both use x and y. So I'm going to take this a and plug it in over here, so I get bx plus 1 plus by over x times y equals 0. So what I'm trying to do here is come up with, if you have a complex number x with x and y, how would you come up with its multiplicative inverse using only that x and that y? So I'm going to take these two equations and I'm going to get a and b in terms of x and y. So then I only need to know my given complex number, and then I can come up with its multiplicative inverse. So with this equation here, I'm going to start to solve it for b. So we're just going to do basic algebra here. So we're going to distribute this y, and let's see what we get. We get bx plus y plus by squared over x equals 0. Then I'm going to keep the parts that have a b on the left side and move the parts that don't on the right side. So that'd be bx plus y squared over x equals negative yx. And then isolating b, we get negative y over x squared plus y squared. So now I know what b has to be using only x and y. So this b, which is part of the multiplicative inverse, to come up with it, I only need to know what x and y are. Well, now that I know b, I can come back over here and figure out what a would be. So a equals 1 plus by over x. So I can plug this in for b over here. And we get a equals x over x squared plus y squared. So what that did for me is, if I'm given any complex number, I just need to know its real and imaginary parts, and I can come up with its multiplicative inverse relatively quickly now, because its inverse will be this number right here, a, plus this number, b, times I. So therefore, for any complex number, we now can come up with its multiplicative inverse as a plus b I. So now I have a little formula that can give me its multiplicative inverse. So let's give that a try. So let's find the multiplicative inverse of 2 plus I. So z equals 2 plus I, which means its real part is 2 and its imaginary part is 1. So its multiplicative inverse would be 2 over 2 squared plus 1 squared plus negative 1 over 2 squared plus 1 squared I, which would be 2/5 minus 1/5 I. So that would be its multiplicative inverse. So let's check that that actually is the multiplicative inverse. So if we take z times its multiplicative inverse, we'd have 2 plus I times 2/5 minus 1/5 I. So we would get 2 times 2/5 is 4/5. And then we'd have minus 1 times negative 1/5 plus, let's see what its imaginary parts would be. We'd have 2/5 I minus 2/5 I. So we'd have 4/5 plus 1/5 is 1, and then 2/5 I minus 2/5 I would be 0, so we end up with 1. So this does actually multiply together to give us positive 1, which is the multiplicative identity. All right, we got a few more laws. So now that we have addition and multiplication, the commutative law, as you're used to in the real numbers, holds true in complex numbers. So if you have the sum of two complex numbers, z1 plus z2, you can change that order and they're still equal. So z2 plus z1 is the same thing. And you also have a commutative law for multiplication. So z1 times z2 would give you the same thing as if you did z2 times z1. So you can alter the order of addition and multiplication. And the associative laws also hold true just as you're used to from the real numbers. So if you have z1 plus z2 plus z3, you'd get the same thing if you added z1 and z2 together first and then z3, or if you did z2 and z3 together first and then z1 after that. And same thing with multiplication. So z1 times z2 then times z3 would give you the same thing if you did z2 times z3 and then multiplied by z1. So the commutative and associative laws work exactly the same as you're used to in the real numbers. All right, so to wrap this up, this first lesson up, just make sure you understand that the complex numbers are simply an extension of the real numbers. So the real numbers are part of the complex numbers. So to see that, consider the any complex number of this form. If you just had x plus 0i, then you would just have z is equal to x. Well, x is a real number, making z a real number. So any complex number where the imaginary part is 0 is simply a real number. So that's letting us know that the real numbers are part of the complex numbers. Well, if you have the real part be 0 and the imaginary part not be 0, then you get what's called a pure imaginary number, meaning there's no real part. It just has an imaginary part. So the real numbers and the pure imaginary numbers are part of this bigger set of numbers called the complex numbers. So the real numbers and the pure imaginary numbers together make up what's called the complex numbers. All right, well, let's just see some of these things in action real quick. So let's practice with addition. So if z1 is equal to 1/2 minus 2/3 I, and z2 is equal to 4 plus I, let's add those together just to see two specific ones added together. So z1 plus z2 would be 1/2 minus 2/3 I plus 4 plus I. So if you combine the real parts, you'd have 1/2 plus 4, and then combine the imaginary parts, you'd have negative 2/3 plus 1i. Well, you'd have, let's see, you'd have 9/2 as the real part, and 1/3 as the imaginary part. So the sum would be 9/2 plus 1/3 I. Well, in B, let's practice multiplying two complex numbers. So if we multiply those together using our definition, again, you can kind of think of it as distributing. So you could take 7 times 1, and then you're also going to have negative 21i and a positive 2i, and you're also going to have a negative 6i squared. So remember, the way this works is the 7 times 1, that's part of your real part of the product. And then when you take 2i times negative 3i, you're going to get negative 6i squared. So the I squared is negative 1, so you get negative 2 times negative 3. So that'll give us the real part. The imaginary part comes from the fact that you're going to have to do 7 times negative 3i. So you're going to get 7 times negative 3i, and then 2i times 1. But they all had an I with it. So you get 7 plus 6 is 13. And then the imaginary part, you're going to have negative 21 plus 2, which would be negative 19. And then one more time, let's find the multiplicative inverse of a number. So the multiplicative inverse of 3 minus 5i would be x over x squared plus y squared plus negative y, x was 3, then it'll be x squared plus y squared I. So we get 3 over 34 plus 5 over 34i. That would be the multiplicative inverse. And let's verify that that multiplies together to give positive 1. So z times its inverse, we'd have 3 minus 5i times 3 over 34 plus 5 over 34i. So we're going to get 9 34ths minus, let's see, negative 25 34ths. So that'll add together and give us 34 34ths, which is 1. And then we're going to get 15 34ths I, and then a negative 15 34ths I, which will be 0. So that does come out to be positive 1. Okay, that wraps up our first introductory video. And in the next one, we will discuss subtraction and division.